Hello. In the last class, we have learnt boundary value problems with the derivative boundary conditions. Okay. So, now let us learn higher order boundary value problems. Okay. Higher order BVPs. So, let us start with an example first. Consider this equation. Okay. So, y dash of 0 is 1 and say y of 1 is minus 1. Okay. Say h is 1 by 3. Okay. So, now with usual discretization, one must obtain for y 3 what should be the corresponding approximation. So, we have done it in the first lecture. So, accordingly y 3 is approximated as minus 2 y I is 3 x I square. Okay. So, now if we run this equation for I 1, okay, y 3 is 2 y 2 plus 2 y 0 y minus 1 minus 4 h cube y I 6 h cube x 1 square, and at I 2 2 y 1 and this will be y 0 minus 4, this is y 1, y 2 6 x 2 square. So, what was our line? Our line was x 0 is 0 and x 1, x 2, x 3 is 1. So, we have the following fictitious values. Which are corresponding to the nodes outside the actual grid. Okay. So, now let us look at the boundary conditions. Okay. So, the boundary conditions, this is y prime. Okay. So, let us discretize the boundary conditions. So, we start as follows. So, these are fictitious. Okay. Then we y dashed of 1 is minus 1, this is y 4 by 2 by 2 h minus 1, this implies okay. Then we have y 0 equals to 1 and then y dash of 0 equals this implies okay. So, we have these two fictitious values. Okay. Now, if you look at suppose we call this A, this y 0 is explicitly given. So, this gets determined. Then we have y1, y2, y3 there. So, y0 gets determined. So, y1, y2, y3. So, 3 unknowns. Then this fictitious value is determined and this is determined. However, ABC is not tridiagonal. So, that means there is some issue with respect to the number of unknowns and number of equations. Okay. Well, following the earlier strategy, suppose we write A at I equals to 0, I equals to 3, we get y minus 2 and y 5, which are fictitious. So, that means one cannot adopt the earlier strategy, like you run the equation earlier in the sense which we have done with the derivative boundary conditions. So, one cannot adopt the similar strategy because in a sense of recursive manner you get number of fictitious values. Okay. If you run further I minus 1 I 4, so you get more fictitious values. Okay. So, so this strategy does not help. Okay. So, let us look into more general case. Okay. So, this is more general case. So, we consider third order linear equation given by y 3 plus. So, when I said general, we have all the terms. So, that makes life little complex. So, 3, 2, 1 and y 0. So, all the terms are there, and since it is a third order equation, we need a 3 boundary conditions. So, y of a is alpha, gamma. Okay. So, the grid points x n x n plus 1 equals to b. Okay. Now, what are the approximations? So, for first approximation, second, and for the third, okay, for the third. So, now with these approximations, okay, so one gives say a xi. We get this, and boundary conditions y0 is alpha, it's beta, okay. So, as I mentioned, 4 and 5 is not tridiagonal system, okay, right. When we write 4 at I is 0, n, we get the fictitious values okay. So, these are the fictitious values. Okay. However, one can obtain 3 equations. So, already we have okay. We have 3 equations from the boundary conditions 5. Still we are left with one more, that is one more equation. Okay. So, how do we supply? So, here we bank on the order of the equation. See, the order of the equation is higher order, and we know how to reduce it to a system. So, we use this, let y dash is p, then we get the equation and correspondingly y of a is alpha and p of a is beta and p of b is gamma. So, that is how our system gets reduced. Now, what we do is we discretize now the new okay. So, what kind of discretization we propose? So, discretization of nu as follows. So, this we discretize. So, backward there. So, this is average or some trapezoidal integration. So, this is for P, okay. And for other equation, usual central, so okay. So, what did we achieve? We will see what we have achieved. We have taking on the higher order equation, we have converted into a system. So, this serves as one more equation. This serves as the one more equation that we require. Okay. So, let us see how we proceed. So, from 6 we have okay, and 7 sorry A I Y I this is A I Y I plus B I P I minus 1 plus C I P I plus D I look at that. This contain P I minus 1, P I plus 1 and Y I. Okay. So, this is written in this form, okay, where A I is C of x I, B I is and so this can be verified very easily. Okay. Now, we have to somehow adjust the number of equations and the number of unknowns. Okay. So, how do we do it? Let us proceed step by step. Okay. So, let us write down 6 and 7 for I equals to 1. So, sorry 8, this 6 and 7 means or 8 and 9. Okay. So, from here when we write for I equals to 1, y 0 plus h by 2 p 0 y 1 p 1 equals to 0, and from here a 1 y 1 b 1 p 0 c 1 p 1 d 1 p 2 okay. So, these can be written as how did we do that? Look, we have y 0 alpha and p 0 is beta. Okay. So, these are known. So, we have pulled it to the right hand side. Okay. Then from the other one, okay. Then we have to be careful. So, what I have done, these two 8 and 9 we have written for I equals to 1. Okay. Now, these two, that means these two we need to run from 2 onwards, right. So, let us look at it. If we run for 2 y 1, then p 1 y 2 p 2. Okay. So, you have from this we have a vector. Okay. What is the vector? Y I p I kind of vector. It is, see, look at it, y I minus 1 p I minus 1 y I p I. Okay. So, at least the index is matching, but whereas here there is a slight deviation. Okay. Because y I p I minus 1 p I plus 1. Okay. So, let us look at it how we can place this. Okay. So, now for okay. So, this can be written as, you introduce some notation. Let us introduce notation x n is x I x I y I p I. Okay. So, if we introduce this, okay. So, in general any x n is y n. Okay. So, there is a coefficient. If you look at it, suppose look at this equation, y I minus 1 p I minus 1. If we would like to reproduce this, coefficient of this must be 1 there and coefficient of this must be h by 2 there. Okay. Then similarly for y I, and Pi. Okay. So, that means from here if we pull out for y I minus 1 there is no coefficient. Therefore, we expect 0 there, whereas for Pi minus 1 we have Bi. So, what did we achieve? These two equations so two terms we have produced and these two terms yes we have produced. So, that means these two equations can be put in a matrix form. So, this further can be 1 h by 2 0 Bi and as per our notation this can be x I, where x I is x I minus 1, sorry, y I minus 1, Pi minus 1. Okay. So, what we are going to do? We have to follow very carefully these two equations for 2 to n, we are trying to put it in the matrix form and with a vector notation. Okay. So, if we do that, we get this can be written as A I plus B I plus C I equals D I and what is our notation? X I then we should be able to write down the matrix A. So, again I go back x I minus 1, which means y I minus 1, P I minus 1. So, we need the coefficient matrix A I for this. Okay. So, what should be A I? The coefficients coming from first equation, the corresponding coefficients from second equation. Okay. So, which already we have written down, look at it. So, here 1 comes and from here h by 2, from here there is no y I minus 1, therefore 0 and we have for P I minus 1 we have B I. Okay. So, this must be our A I. Okay. So, what was our A I? 1 h by 2 0 B I. Okay. Let us look at next we need B I x I and what is x I? Y I P I. Okay. Okay. Look at that. So, here we have minus 1 okay, minus 1 for y I, h by 2 for P I. So, which means this minus 1 there, h by 2 there, this is multiplying y I P I. Look at this and what is multiplying here? Here A I is multiplying y I and C I is multiplying. Okay. So, we are getting the corresponding coefficient. So, the two equations in the matrix form. Okay. So, B I must be minus 1 okay. Then Ci, okay, xi plus 1, xi plus 1, look at that. So, here we do not have any yi plus 1, pi plus 1. So, the first entries must be 0, whereas here we have pi plus 1. Okay. So, therefore, so I am not explaining like this, because it is straightforward now. There is no yi plus 1, pi plus 1. So, the first entries must be 0 in the matrix, but whereas here there is no yi plus 1. So, the first entry in the second row must be 0 and we have di there. Okay. So, correspondingly Ci must be 0 0 0 di, because it is multiplying xi plus 1. Then di, di must be column matrix. We have exhausted all the terms here and then the third one, there is nothing on the right hand side, whereas here we have this term. Well, this d is notation wise, this is matrix, this is the known function. Okay. So, these are our equations, and this from I 2 3 n minus 1, and these are how many? N minus 2 equations. Okay. But we had written something for 1. So, for 1 we have written. So, this also can be put it in matrix form probably. Okay. So, let us put it. Okay. I equal to 1 case can be written as b 1 x 1 c 1 x 2. Okay. So, we have to give some number 12, but 10 and 11 I equals to 1, 10 and 11. They can be put it like this. How? Look at that. Here we have y 1 p 1, which is nothing but exactly our vector x 1. Okay. So, from here y 1 p 1 is a 1 c 1. So, our matrix B is more or less structured. So, B 1. So, B 1 minus 1 h by 2 a 1 c 1. This is a small c coefficient. Okay. Then the matrix C 1, we do not have the next, because C is multiplying x I plus 1. So, when I is 1 x 2, but we do not have any 2 terms there. So, we get 0 0 and 0 d 1 and d 1 is minus alpha minus h by 2 beta minus b 1 beta plus h square d of x 1. Okay. So, this is 13. Okay. So, this is 13. Now, we have covered I 1, I 2 to n minus 1, then we are left with, yes, you are right, left with I n. So, now I n case gives us however. So, from where would we get this? Of course, from here. Okay. So, the matrix, okay. So, this can be put it as a n x n minus 1 where see x n minus 1, that is y n minus 1 p n minus 1. So, we have the terms very much 1 and here we do not have y n minus 1. So, p n minus 1 has the term, okay. Then b n, look, the remaining left out, we know p n. What was p n? It's gamma. Okay. This is a boundary condition, because y dash of 1, which is p n. So, this term is gone to the right hand side of d n. So, we can expect minus 1 there and there is no as such p n left. So, 0 there, whereas here we have y n and p n plus 1. Okay. So, we had, please look at carefully. Okay. So, this is n minus 1. So, y n minus 1, p n minus 1 is done. Then x n. Okay. So, we have to write x n. So, x n should contain y n and p n. Okay. So, p n is known. So, we push it to the other side and even here we know it. So, this will be a n d n with a definition x n equals y n p n plus 1. Okay. Because this is known to us. So, we push it to this side. Okay. So, therefore, unknowns y n and p n plus 1, that is. So, it is a small adjustment. So, you make a note of this, because its symmetry is lost. Okay. So, then we are in a position to, so d n must be, p n is known. So, it has gone minus gamma by 2 okay, H, and here we know this is gamma. So, minus C n gamma okay, right. So, we have let us compile n minus 2 equations, then this is another equation. So, n minus 1 and this is another one equation. So, total n equations, okay. But in what sense? So, they are n minus 2 plus 1 plus 1 and each is 2 equations, right. So, 2 n equations in how many unknowns? Okay. 2 n unknowns, because these are 2 and these are 2 times n minus 1. So, what is the achievement by putting in this matrix form, by converting into system? The number of unknowns and the number of equations have been matched. So, now eliminating the unknowns, okay, we get, let us see carefully, look at this. So, it is for 1 to 2 to n minus 1. So, then this is for the 1. Okay. So, if we write a matrix, these are all matrices, right. So, suppose somebody writes B 1 and a C 1 there, this must multiply, let us say in a bigger matrix, these two must multiply x 1 x 2. Okay. Then 2. So, for 2 to n minus 1, it is like this. Okay. So, let us start the index to a 2 must multiply x 1. So, that means we must expect a 2 there, then B 2 must multiply x 2, B 2 there, then C 2, okay. So, this continues, each of them is a column vector. So, for example, what is x 1? And what are they? These are matrices in turn. Okay. So, this corresponds to n equals to 1 and I equals to 1 and I 2 to n minus 1, and the last what we obtained, the last one I equals to n. So, this will also come at the bottom, and this entire thing, which one I am talking about? This you see it is a blocks, but then again it is a tridiagonal system. So, it is a block tridiagonal system. Okay. So, we get as follows: A x equals to d, some global where the structure of A follows from the earlier matrices these are null matrices, then A 2, B 2, C 2 like this. Okay. And what is our x? It is better I write x. X look like this. See, x 1 is x 2. So, this is our x, okay. And so, this is in fact, I should write here, because this is a block tridiagonal system. Okay. So, with reference to higher order BVP, what did we do? If you discretize the equations, definitely we are short of one equation, and then this has been supplied by really writing the higher order equation in terms of a system. Okay. So, this system will help us to supply the additional one more equation, and since it is a system, we have to solve simultaneously. So, we obtain a block tridiagonal matrix. So, let us try with an example. Okay. So, this simplest okay. So, for calculation purpose, I have taken h equals to 1, say 0, 1, 2, 3. Okay. So, then with the usual discretization, so discretization of this 0, discretization of this because 2 in the denominator. So, that goes there. Okay. So, now we write 1 at I equals to 1. Okay. So, this then I equals to 2. Okay. So, however, here and from boundary condition we have Okay. So, this gives us so for example, in this y 0 is given and y minus 1 can be substituted, y 4 can be substituted. So, this whole thing leaves us with y 1, y 2, y 3 as unknowns. Okay. So, now at I equals to 0, y 2, 2 y 1, y 0, at I equals to 3, so what happened? So, these are new fictitious. So, two equations. So, because these are all redundant. So, now this reduces to two equations, but y 1, y 2, y 3 and so 5 unknowns. So, we have to really depend on y dash equals to p. So, then p double plus y is x. So, correspondingly this one and p of 0 is 0. Okay. So, with the discretization of this we get so that means discretization of this, Okay. So, and then we have let us have some number. Okay. So, I equals to 1, A gives us 2 y 1 minus p 1 is 2, because I have simplified, I have just used, you can do it. Okay. Then B gives us okay, right. So, this is we have done it for a general case. So, now for this A and B for I 2 and 3. Okay. So, this can be written as, in fact, I 2 only one we have, because our grid was 0, 1, 2 and 3. So, this is x 0, x 1, x 2, x 3. Okay. So, this can be written as d I, right. So, if we try to do that, we arrive at So, this is one set and another set. Okay. So, ultimately so we get another matrix here and this one. So, this will be the tridiagonal system which we have to solve. So, this gives the structure for the higher order boundary value problems. So, like initial value problems, higher order one can reduce to system and then solve it. Similarly, here we have been reducing to system to support one more equation, but then we end up with a block tridiagonal system which one can solve it. Okay. So, there are other methods for solving nonlinear boundary value problems. So, we will look at them in the coming lectures. Until then, bye.